Okay, so 3.1 was about measures of center. 3.2 is about measures of spread. Actually, it's more than anything, it's about the standard deviation, which is a measure of spread for sure. Um, but that's what we're going to spend most of our time in this section talking about, is the standard deviation. So to get us thinking about this, what I have here are some dot plots, and dot plots are kind of like bar charts, only instead of drawing bars, we draw a dot for each, observation. And these dot plots represent the number of chocolate chips in chocolate chip cookies for Subway data, for some Subway cookies, and for some Quiznos cookies. I don't even know if Quiznos sells chocolate chip cookies, but we're just going to pretend, okay? Now, if you look at these two data sets, they're obviously very different data sets, okay? If you were to compute the sample mean number of chocolate chips for each of these sets of data, you would find that they have the same mean, right? The sample mean is about 24 chocolate chips per cookie. However, they're very different. The Subway's cookie data is a lot more spread out than the Quiznos cookie data. Or another way to say that is that the Quiznos cookies are a lot more consistent with the number of chocolate chips they have. Whereas with the Subway data, it's like, yeah, you could have a chocolate chip cookie with 30 chocolate chips in it, but you could have one with only 19 chips in it, right? So the Subway data is more unpredictable, whereas the Quiznos data is pretty consistent. So the data sets have the same mean. They have the same mean, but they are obviously very different data sets. And what's different about them is that the Subway data is a lot more spread out. It's more unpredictable, right? It's less consistent. So we'd like a way to be able to describe that spread numerically, okay? So the first way that we might think about doing this, kind of a naive approach, would be to look at the range of a set of data values, right? So the range is the difference between the maximum value and the minimum value. And at first glance, it seems like, oh yeah, this is gonna be a good measurement of how spread out the data is. After all, if we look at the range of the Subway data, I'm gonna call it range sub S. If we look at the range of the Subway data, well, it would be the maximum 30 minus the minimum 19. So 30 minus 19, which is 11, right? Whereas if we look at the range of the Quiznos data, we would say, well, it's 25 minus 23, which is 2. And so looking at that, you're like, oh yeah, so this is a clear indication that the Subway data is more spread out than the Quiznos data. And for this particular situation, that kind of captures what it is that we're looking for. But imagine that the following were to occur. So imagine that 2 more Quiznos cookies are sampled, and that one of the cookies just so happened to have 19 chocolate chips and the other just so happened to have 30. So going up to the dot plot, it's like we'd have this situation now with an additional cookie there and there. So now the question is, what is the range of the Quiznos data now? Well, the range of the Quiznos data now is maximum 30, right? Minus minimum 19, which is 11. So the Quiznos data now has the same range as the Subway data, even though when you look at this data set, even with these 2 new cookies thrown into the mix, the Quiznos data is still more consistent, right? It's still more grouped together than the Subway data is. So probably the range isn't good enough, right? Like it's not a very good measurement of how spread out data is. Another thing is that the range is not resistant, right? We added a large and small value, and the range changed pretty drastically. So is the range a resistant numerical summary? No. How good would you say the range is at describing the spread of a data set? Not very good, right? Not very good. We'd like to be able to distinguish between this kind of data set and this kind of data set, okay? And the range just doesn't quite do that for us. So, so we need a better numerical summary of the spread. One good idea would be to try to find how far on average each observation is from its mean. And that's essentially what we're going to do with the standard deviation. So sort of loosely speaking, the standard deviation is a measurement of how far on average each observation is from the mean. So, so let's see if we can come up with a formula for that idea. Okay. So if we want to figure out how far on average each observation is from the mean, then the first thing we would need to do is figure out how far each observation is from the mean. So we need to find the each individual distance, right? And those things are called the deviation about the mean. So to compute the deviation about the mean, we're going to say, well, if xi is an observation and x bar is the sample mean, then a deviation about the mean is going to be xi minus x bar. Okay. For example, okay. So let's say that we have this data set here. And let's find the deviation about the mean for each observation in the set. Okay. In order for us to do that, the first thing we would need to do is find the sample mean, right? So we'd have to say, well, okay, so x bar is 0 plus 1 plus 2, right, all the way up to 6, divided by 1, 2, 3, 4, 5, 6, 7, 8, 9. And I think this mean is 3. Let's see, 1 plus 2 plus 3 plus 3 plus 3 plus 4 plus 5 plus 6. Yeah, divided by 9 would be 3. So the sample mean is 3. So now if we want to find the deviations about the mean, so these are our observations, right? This is the data. The deviations about the mean would be xi minus x bar. Okay, so if I do 0 minus the mean, 0 minus 3, that would be negative 3. If I do 1 minus 3, that would be negative 2. 2 minus 3 is negative 1. 3 minus 3 is 0, 0, 0. 4 minus 3, 5 minus 3, 6 minus 3. Okay, so those are all the individual deviations about the mean. Now, once we have these individual deviations about the mean, remember that our goal is to try to come up with the formula for the average deviation about the mean. So what we want to do now is find the average of these deviations. But when we go to compute that average, we have a slight issue, okay? Because when we try to compute the mean of these deviations, we get negative 3 plus negative 2 plus negative 1 plus 0 plus 0 plus 0 plus 1 plus 2 plus 3, and then we would divide by 9. But the numerator of that expression ends up being 0, right? And anything divided by, or 0 divided by anything is 0. So the average of the deviations about the mean that we're coming up with is 0, which isn't good, because the whole idea that we're trying to capture is how far on average are the deviations from the mean. To say that they are 0 units away from the mean on average is that the only way that could be true is if all of the observations were the same exact number. So obviously something went wrong here. And in fact, it's not just a coincidence. The sum of the deviations about the mean is always 0. Right? It's always 0. Well, so what do we do? Well, we're going to make the deviations about the mean positive by squaring them. Okay, and this way we can be sure that the sum of the deviations about the mean is not always 0. And then we'll calculate the mean of the squared values. Okay, what that's going to do is going to give us the average squared distance, but we didn't want the average squared distance, we just wanted the average distance. So we'll finish off by taking the square root. Okay, so again, we're going to start off by finding the individual deviations about the mean. So the individual distance that each observation is from its mean. Then we're going to square those distances to make the values positive. Then we're going to find the average of those squared values, okay? And then we're going to take the square root of that number. And that, in a nutshell, is what the standard deviation is. So For the population standard deviation, we use this symbol here. This is a lowercase sigma, right? So this is the Greek letter sigma. So it's a lowercase sigma. So the population standard deviation is going to be the square root of the deviations about the mean squared and then averaged. Okay, so you add up all the deviation, all of the squares of the deviations, and then divide by the number of observations. For the sample standard deviation, the symbol that we use is a lowercase s, and the formula is a little different. So notice that here we're dividing by n. Here we're dividing by n minus 1. Okay, so as a warning, right, the sample standard deviation, for the sample standard deviation, we divide by n minus 1, not n. Okay. The reason for that is because, as it turns out, if we divide the sample standard deviation by n instead of dividing by n minus 1, we actually end up underestimating what the true population standard deviation would be. And so we offset that by dividing by n minus 1 instead of n. There's a better mathematical explanation for that is sort of beyond the scope of this course. But if you're interested, you know, you can look up some, like a YouTube video about, you know, the expected value of the sample standard deviation or something, and then you'll get a proof of the fact that you need to divide by n minus 1 instead of dividing by n. One more thing to say before I give you an example. This number that we get inside of the square root, before we take the square root, that's called the variance. So the population variance is just the stuff inside the square root, same with the sample variance. And the symbols that we use are sigma squared and s squared, respectively, okay? And that should make sense, right? If the standard deviation, you know, if the variance is sigma squared, then the standard deviation, you take the square root of both sides of this thing, and you get sigma equals square root of this stuff, right? Same thing with the sample variance and sample standard deviation. So they're related. They're just, the standard deviations are just the square root of the variance, okay? So at this point, your head is probably swimming a little bit, and you're probably like, I have no idea what's going on. What are we even talking about? So let me give you a couple examples, and then it'll be hopefully a little bit more clear. My main reason for walking you through that previous page was just that I want you to understand conceptually what the standard deviation measures, okay? The standard deviation is a measurement of how far on average each observation is from the mean. If that average is really large, then it means that the data is pretty spread out, right? Whereas if the average is small, then it means the data is all kind of grouped together close to the mean. So let's walk through a couple examples. This says compute the variance and the standard deviation of the following sample data, and here's our first data set here. Okay, so in order to compute the variance and standard deviation, the first thing we need to do is calculate the sample mean. So the sample mean x bar is going to be 82 plus 77, and so forth, 6, 7, 8, 9, 10. Let's see what we get. So I get 790 over 10, which would be 79. And by the way, it goes without saying, I mean, you should pause these videos and try these problems out yourself, right? Follow along with me. Do the calculations on your calculator on your own. Oftentimes, students watch me do the calculations, and then they think they can do it, and then they go to do it themselves, and they end up making calculator mistakes and stuff. So work through the problem with me, okay? But anyway, you should get a sample mean of 79. Now, the sample variance, s squared. That's going to be the sum of all of the deviations about the mean squared, okay, divided by n minus 1. Okay, so that's going to be, well, the first observation is 82, right? 82. So it's going to be 82 minus the mean of 79 squared plus 77 minus the mean 79 squared plus 90 minus 79 squared, and so forth. And then we'll do this all the way until we get to the end of the list, which is 88. So we will do this all the way up to 88 minus 79 squared. And then we're going to divide that entire thing by our sample size minus 1. Okay? So let's see what we get now. 82 minus 79 is 3. So this is 3 squared. 77 minus 79 is negative 2. 90 minus 79 is 11. 71 minus 79, negative 8. I'm going to stop talking, or I'll mess myself up. Okay, so I think I got them all on there. You can throw all of this into your calculator at this point if you want. I mean, depending on how comfortable you are using your calculator, you could have just thrown it all into your calculator from the very first step. But I still want to see you write this part out, right? So I want to see at least this much on a test or a quiz. I would want to see you write this part out, and then if you want to just throw it into your calculator and give me the answer, that would be fine. Okay, I'm just going to do one more step here before I punch this into my calculator. So I know I've got 9 plus 4 plus 121 plus 64 plus 17 squared, 289 plus 121 plus 25 plus 25 plus 225, I think. Yeah, 225 plus 81 divided by 9. Okay, so that's 964 over 9, which is about 107.1. Okay, so that's the variance, right? So that's the variance. So that's the variance. So now if you're thinking to yourself, well, that's a lot of work. We don't have enough space now to do the standard deviation, because remember, we were supposed to compute the variance and the standard deviation, right? But the standard deviation, once you have the variance, the standard deviation is just one step, right? Because the standard deviation is just the square root of the variance. Now, my advice would be, don't use this rounded value here, because then you're going to have rounding errors in your answer. Just use the exact fraction value inside of the square root there. So I would say 964 over 9. So square root of 964 over 9. Let's see what we get. That's about 10.3. Okay, so there's the standard deviation. So the variance is 107.1. The standard deviation is 10.3. Okay, approximately. So that's how that goes. Standard deviation, it's a pretty tedious calculation. I'm going to show you in 3.5, I think. I'm going to show you in 3.5 how to use StatCrunch to get standard deviations. But in the meantime, I think it's valuable for you to do the work by hand so that you get an understanding again of what these formulas mean, what the standard deviation is trying to measure. Okay, so it's a measurement of how far on average each observation is from the mean. I think that's probably like the third time I've said that. So that should give you a clue as to how important this concept is. But go ahead and give the video a pause now and see if you can do part B. All right, so same thing, see if you can calculate the standard or the variance and then the standard deviation. Okay, here's my solution. So first of all, we need the sample mean. Okay. Then we can use it to calculate the variance. This should be a sigma, by the way. If you're wondering, what in the world is that symbol he just drew? It's a Greek sigma. Okay, so 6 minus 10, 7 minus 10, 9, or 8 minus 10, 9 minus 10, 10 minus 10, 11 minus 10, 12 minus 10, and 17 minus 10. So you get exactly 12. So this time you get an exact answer for S squared. So the variance is exactly 12. And the standard deviation is going to be the square root of 12. About 3.5. Okay. So there we go, right? So that's that. Moving on. For your information, in case you're wondering, the Subway chocolate chip data had a standard deviation of 2.6, and the Quiznos chocolate chip data had a standard deviation of 0.7. So going back to the front page, remember this is kind of what started the whole conversation, was looking at these two sets of data, and we just said that the standard deviation here was 2.6. And the standard deviation here was 0.7. So okay, so now you can see that, yeah, so this standard deviation is doing a much better job at describing the spread of the data. And generally speaking, the larger the standard deviation, the more spread out the data is, right? So a larger standard deviation means more spread out, more volatile, less predictable, right? Less consistent. A smaller standard deviation means more bunched up, more consistent, right? Less variety, okay? So in general, the larger the standard deviation, the more spread out the data is, okay? So in summary, the standard deviation is a measurement of how spread out the data is. It tells us how far on average the observations are from the mean. In other words, how far they are from the center. A large standard deviation indicates that the data is relatively spread out, like the Subway data. A small standard deviation indicates that the data is bunched up, like in the Quiznos data. The standard deviation is going to be very, very important to us later on in the semester. For right now, one of the uses that we can get out of it immediately is something known as the empirical rule. The empirical rule tells us how much of the data we can expect to fall within a certain number of standard deviations. The empirical rule only applies to bell-shaped data, okay? But for bell-shaped data, we can say that 68% of all data values fall within one standard deviation. Okay, 68% of all data values fall within one standard deviation of the mean. 95% of data values fall within 2 standard deviations. And 99.7% of the data, so almost all of the data, is going to fall within 3 standard deviations. Okay. So, in other words, what we're saying is if you've got a bell-shaped distribution like this, okay, with a bell-shaped distribution, the mean is going to be right in the center. Okay. And if you're 1 standard deviation above the mean and 1 standard deviation below the mean. So if you're within these 2 fences, okay, if you're inside of these 2 fences, then you're within 1 standard deviation of the mean. And what we're saying is that 68% of the data falls within those fences. Okay. 95% of the data falls within 2 standard deviations. So that would be this fence and this fence. Okay, so 95% of the data is going to be within those 2 fences. Okay, and then 99.7%, so almost all of the data is going to be within 3 standard deviations of the mean. Okay. So, which only leaves 3% of the data out here in the tails, right? And it's equally split between the tails. So half of 0.3% is 0.15% here and 0.15% there. So let me give you so number 5, it says, suppose that a random sample of students' IQ scores has a mean of 100 and a standard deviation of 16.1. Further, suppose says redraw the chart from the previous page with the parameters labeled. Okay, they're talking about this chart right here. So we're going to redraw this chart, labeling all of the parameters. And you can do this from memory. The only numbers you have to have memorized are 68, 95, and 99.7. If you can remember those 3 numbers, then you can make this chart from memory. And here's how I do it. So first of all, we give ourselves a little bell-shaped distribution. The mean is going to be right in the center. Okay. In this case, the mean is 100. Oh, actually, we were dealing with sample means here, right? So I should use X bar instead of mu, but same idea, right? So the mean is right there in the center. 1 standard deviation above the mean, mu plus sigma, would be 100 plus 16.1, right? So that's 116.1. 1 standard deviation below the mean, mu minus sigma, would be 100 minus 16.1. 100 minus 16.1 is 83.9. So 83.9. Okay? So in other words, if you have an IQ score between 83.9 and 116.1, then you are within 1 standard deviation of the mean IQ score. Okay? And what we know from the empirical rule is that 68% of people are going to be within 1 standard deviation. So in other words, From the empirical rule, we know that 68% of people have an IQ score between 83.9 and 116.1, right? So 68% of people right off the bat. Now, if you want to figure out how much of that 68% is here and how much of it is here, well, you can use the fact that a bell-shaped distribution is symmetric. So exactly half of the 68% is here and half of it is here, right? Half of 68 is 34. So 34% of the data is there, 34% of the data is there. Okay. So that's within one standard deviation. Within two standard deviations, right? Mu plus 2 sigma. Well, I'm 2 standard deviations above the mean. So if I add another standard deviation, right, 116.1 plus another standard deviation of 16.1, I'm going to end up at 132.2. Okay. So if I have an IQ score of 132.2, then I'm 2 standard deviations above the mean. Okay. In the other direction, mu minus 2 sigma. So we'd have 83.9 minus 16.1. So that's 67.8. Okay. So if you have an IQ score between 67.8 and 132.2, then your IQ score is within 2 standard deviations of the mean. Okay. And we know that 95% of people are going to be within 2 standard deviations of the mean. Okay. Now, if you want to figure out exactly how much of that is here and how much of that is here, well, you can say, I know that 95% is between these two fences, but 68% of it is already accounted for here in the center. So in these two spaces, I must have 95 minus 68. That's 27% of my data. So 27% of it is in these two locations, okay? But it's equally split because this is a symmetric distribution. So it's equally split between these two spaces. So 27 divided by 2 is 13.5. So 13.5% of data is here, and 13.5% of data is there. Okay. And then I'm going to go out one more standard deviation. So if I'm 3 standard deviations above the mean, mu plus 3 sigma, then again I would add another 16.1 and get 148.3. So if I have an IQ score of 148.3, then I'm 3 standard deviations above the mean. Okay. And on the other side, mu minus 3 sigma, that would be 67.8 minus 16.1. That puts me at 51.7. So if your IQ score is 51.7, then you're 3 standard deviations below the mean, okay? We know from the empirical rule, and I've run out of room to draw this, but we know from the empirical rule that 99.7% of the data, so almost all of the data, 99.7% of it, is within 3 standard deviations. So if you want to figure out exactly how much of it is here and how much of it is here, then you can say, well, 99.7% of it is between these two fences, but 95% of it is already accounted for in the middle. So that means the remaining 4.7% is in these two places, and it's equally split, right? So half of 4.7 is 2.35. So 2.35% data is there, 2.35% data is there. Okay. And then finally, to figure out how much of the data is in the tails, well, we know that 99.7% of the data is within these two fences. That means the remaining 0.3% of data is in the tails, and it's equally split. So half of 0.3 is 0.15, right? So 0.15% there, 0.15% there. Now, if you are completely lost at this point, then my advice would be rewind the video and rewatch the explanation, okay? at some point you just have to sit down and learn the information. Okay. Um, so that's that. Now, the good news is that once we have this chart, answering questions about it is super easy, right? Like part B asks us, an observation is within 2 standard deviations of the mean if it is between what values? Well, you're within 2 standard deviations if you're between mu minus 2 sigma and mu plus 2 sigma. Those values would be 67.8 and 132.2. Okay, so in other words, right, 95, yeah, 95% of people are going to have an IQ between 67.8 and 132.2. Part C says, what percentage of students have an IQ between 67.8 and 132.2, right? What percentage of students are between these two values? Well, for one thing, we know that if you're between 67.8 and 132.2, then you're within 2 standard deviations of the mean. And the empirical rule tells us that 95% of data is going to be within 2 standard deviations. So what percentage of students have an IQ between 67.8 and 132.2? Well, that would be 95%. Another way you could arrive at that same answer would be, since you have this chart already, you could just add these numbers up, right? 13.5 plus 34 plus 34 plus 13.5 equals 95%. That's how we're going to tackle the next one, right? The next one says, what percentage of students have an IQ between 67.8 and 116.1, right? 67.8 and 116.1. So they want to know what percentage fall within this region, okay? So we're going to add up 13.5 plus 34 plus 34. And that's 81.5. Okay, so 81.5. Now, if you're thinking to yourself, well, couldn't I have just said 68 plus 13.5? And the answer is yes, of course, right? There's more than one way to skin a cat. But yeah, as long as you're getting 81.5. Finally, part E asks, what percentage of students have IQ scores below 83.9? So below 83.9. So on part E, we're looking for this stuff, right? Below 83.9. So that would be 13.5 plus 2.35 plus 0.15. So that should be 16%, I think, on the money. Okay, and that's that. That's the empirical rule. So this is my advice. On the homework, when they start asking you questions about the empirical rule, usually they're not going to ask you to draw the chart. Usually they're just going to start asking you questions like this. My advice would be draw the chart. Once you draw the chart, these problems are going to be super easy. Okay, so even if they don't ask you to draw the chart first, and then answering the questions is going to be super easy for you. Okay, that's it for this section. The last page is just a list of the symbols that we've discussed so far. You need to commit these to memory. I'll give you formulas and stuff on the test. Like, you know, I'm going to give this to you on the test. I don't expect you to have it memorized, right? So I'll give you the formula for the standard deviation, but you need to know what the symbols mean, right? You need to know, in order for you to be able to use this formula, you need to know what X bar stands for. You need to know what N stands for, right? So you've got to commit this stuff to memory. It should be like breathing. When you see mu, well, first of all, you should know that that's how it's pronounced. And second of all, you should know that that means the population mean, right? You should just know this. Like I said, it should be like breathing. So you can make flashcards out of this. I mean, whatever you want to do, but yeah, you've got to commit these symbols to memory. Commit them to memory, and know what they stand for. Okay, know what they're measuring. Okay, so that's that. Here's your homework assignment. I'm asking you not to use StatCrunch on these problems, okay? I will show you how to compute standard deviations in StatCrunch in section 3.5, but until then, don't use StatCrunch. Just do the problems by hand. It'll be good for you to develop your intuition and develop your understanding of what the standard deviation is and what the standard deviation measures.